Okay, in the next subsection, I want to start looking at the linear time suffix sorting algorithm. These are among the most recent results we'll talk about in this class. They're at least from this millennium. There are several such algorithms. This is the one that's, I think, most reasonable to explain. It's quite practical. You can implement it to run really fast. So it's a really nice and good algorithm. It's not the latest and greatest potentially. You can tweak it further. But the point of this section will be to show you how you can do suffix sorting in linear time on the theory side if you want. And there's implementations in libraries that can do that play a few more tricks to make it a tiny tad faster than that. Before we go to the algorithm, I have to introduce a second concept that just makes it much easier to describe the algorithm. In fact, instead of L, the suffix array, so L stands for leaves, the leaves of the suffix tree from left to right. Instead of L, we'll compute R in the algorithm, which is for rank. That's the rank array. You can think of that as the inverse permutation of the suffix array. The suffix array is a permutation. I didn't point that out, but it has all the numbers from 0 up through n exactly once in some scrambled order. So you can also talk about the inverse permutation, where if the value at position r in the leaf array, in the suffix array, is I, then we'll get the value r at position I in the rank array. It's just reversed. The definition of this was that this starting position I, the suffix starting at I, is the rth smallest in lexicographic order, right? And another way to say that is that Ti has rank, zero-based rank R. And so that's what will be in the rank array. If you have the starting position, the rank array tells you how many other suffixes are before that in the alphabetic order. And the other way around, if you want to find what's the fifth smallest, then the leaf array can give you the starting position. That's how you go. All right, maybe remember this picture, and hopefully then my many mnemonics for left and right will help you remember this. So you write down the text, all the suffixes, first the whole text, then you leave off one character at a time. So try to remember this triangle. Then I is sorted. That's the starting position of the suffix. I'm leaving off one more character each time. And now the rank array tells you where to find this thing on the right. What's on the right? On the right, you have the same suffixes, but in sorted order. So we know here that the ranks are in sorted order, and L tells you what's the starting position of that rank. So for example, I don't know, which one do we take? This one? L of 8 is 4, which means the 8th smallest suffix, second largest, starts at position 4, index 4. And so if you go to the left, at position 4, you find the same string, naban. And similarly, if you want to know how many strings are smaller in lexicographic order than the entire text, you would look at r of 0 and find, okay, it goes to position 6 on the right, so there's 6 things that are smaller. Fine so far? I spent so much time on this slide because I want you to memorize these two things. So leaf and rank array, they're inverses of each other. The important bit is to remember which one's which. All right. Good point. Yeah, let's not just rely on you memorizing. Let's actually test. So a silly number of answers. They're not really there to trick you. It's just about memorizing the picture. Okay, let's wait till 25 again. Oh, there we go. Okay. It's slow, but eventually works. Okay. So, just briefly, I said this before, right? L lists the leaves from left to right. There's so many L's in that sentence. Hopefully that sticks. And R does not. Simply said, L also lists the indices of suffixes in lexicographic order. R is a different beast. That's the defining relation between L and R, inverse permutations of each other. Maybe you can memorize it that way. So L stands for leaf and left, going left. So in the picture from before, you had suffixes in text order, suffixes in sorted order. So going left means using L. R stands for rank and right. Going right is using R. That's what going right, going left. Okay. Now, lots of you got this right. These two, okay, this is, I don't know if that's correct. I'm telling you, it can stand for that. Hopefully it helps. All right. Now it's time to present the big picture of the linear time suffix sorting algorithm. It's called the Skew algorithm, or DC3 for difference cover 3. We don't have to worry about that. It's just the name under which you will find it. It has 3 steps, and it's basically a divide and conquer style algorithm, like we've discussed a few at the end of section 3. Let me describe the 3 steps. So the first is we recurse on computing some of the rank arrays. So remember I told you we're eventually interested in the leaf array, the suffix array, but it's more convenient to compute the rank array, the inverse permutation. We can always compute one from the other in linear time with a simple loop. R1, 2 are the ranks of all the suffixes that start at positions in the text that are not a multiple of 3. Why that super weird definition? Bear with me a bit. But you're just out of 3 consecutive indices, 3 consecutive starting indices for a suffix, you take 2 and you leave out the third. That's how you go. Then you determine the rank array for these guys recursively. From that, I'll show you how we'll be able to do that. You can induce the ranks for the other ones, the ones that do start at multiples of 3, without spending a lot of extra time. There will be some tricks involved, but that's the second step. And the third step is merging those two. So you have the position, you have the ranks among all those and among all those, but you can't directly translate. So you still have to merge the 2 sorted orders into the full rank array R for the entire input. Now, before we worry about how to do these steps, let's have a quick look at the running time, how this can eventually be linear time. What you'll have to believe for now is that step 2 and 3 are taking linear time in the length of the text. And we'll come back to that. If you take that for granted, then we're overall in good shape, because then the total complexity is linear for the topmost recursive calls doing steps 2 and 3. Plus, we recurse on something that has roughly size 2/3 n. So in the first recursive call, we'll do again another round of steps 2 and 3, but on an array that's just 2/3 n long, or a string. And we keep going like this. So you have this geometric series. Of course, we stop at some point when 2/3 to some power times n is less than 1. So you can write it as this, you can upper bound it by this infinite sum where we keep cutting into 2/3. And even this infinite sum is upper bounded by 3n, so that's your standard geometric series. We've used a similar argument for the rank selection algorithm, where I showed you this square spiral, maybe you remember. That's effectively the same argument. So assuming that we can do steps 2 and 3 in linear time, we're in good shape. And once we have R, we can easily get L from it. And in fact, we'll do this in between in the different steps. Whenever we have computed R, we can easily get L in linear time. That's a simple loop to invert the permutation. Let's first have a look at step 2. So we assume that we already know the relative order of all the suffixes that start at indices not a multiple of 3. And we try to get the relative order of all those that do start at multiples of 3. That sounds super weird, but if you just pick some, if you just look at some examples, it becomes a bit more clear, I think. So suppose we want to take the entire text, otherwise known as T0, and T3, the suffix that starts at position 3. How could we compare those two, knowing or using the knowledge we have about these other suffixes? Well, simple trick. Every suffix is another suffix with some additional character in front. So if we just get rid of this, then we turn that into T1 and T4. And 1 and 4 are not multiples of 3, right? So we can use the information about T1 and T4 from the R12 array to decide which of these two following parts is smaller in lexicographic order. And so we only have to take care of this one additional character that we prepend. And there's really two options, right? Either the first character already decides if T0 is smaller or T3 is smaller, then we're fine. Or the first character of these two is equal, and then we have to look at the suffixes, but we know how they compare. So everything's done. In short, T0 comes before T3 if and only if this ordered pair, so the first character and then this number, the rank of the following part, comes before this pair, another character and a number. And that's it. Okay? Now, this only allows us to compare two things. That's not the same as sorting yet. To get this into the full linear time solution, we have to apply a trick about sorting that we've seen before. So before we get to that, let me do a concrete example and show the step that I've illustrated on two suffixes for all the ones that we need. And so I just thought for this one, it's useful if the example is not too small so that you can see things in action. But I don't want to go through reading all these strings. So we have our text, Hannah Bands Bananas Man. We add a few more dollars just to be sure that when we're cut with multiples of 3, that we always have enough dollars at the end to sort things out. That's for convenience. Here are the strings that we want to sort. These are the ones that start at a multiple of 3. Here are all the other strings, and we assume recursively we know how they are sorted. What's the sorted order? In particular, we have the rank array given here. Now it's listed in this weird order because here they are in the sorted order. I should have maybe put it on this side. All right. So far, so good. So what we're doing now is try to get these sorted using that knowledge. And so we replace, I don't know if you can see this, maybe a bit too subtle. I split off the first character and then the rest slightly. So we copy the first column here. That's just the first character of all those suffixes. And then the rest of that suffix we replace by a number. And the number is the rank of what's left. So for example, in this case, T15, when I split off the first character, it's T16, what's left, the S-man part. Then I look up rank of 16 is here. So I find that's 14. So I take that rank and put that as a number here. And the last slide hopefully convinced you that this retains the relative order of all those. And the way to sort those is using 2 rounds of radix sort, which is you first sort by the first component, and then within those that are equal by the second component. Now, the trick why we do this is that we can do it in linear time using counting sort. Because in both cases, we're effectively sorting integers. The first column is individual characters. Now we have letters written there, but you all know they're ASCII characters. They're converted to numbers anyways in a computer. And the second is pure strings from the start. Also, the numbers are within a reasonable range. Because they are ranks, right? These go from 0 up to what the number of these is, which is 2/3 n. So we won't run out of bits in our word RAM or something like that. The numbers are not too big. They're within 0 and n. Okay? So we can do this with 2 rounds of counting sort in linear time. And from that we get our rank array R0 for all the suffixes that start at a multiple of 0. Questions about this step 2, inducing the ranks for R0? If not, let's look at the second non-recursive step, step 3, which is assume we have R0 and R12, which is effectively giving us the sorted order of these green and blue suffixes. I have these separate now at the moment. The green ones are those that start at multiples of 3. The blue ones are those that start at an index not a multiple of 3. And we'd like to merge these 2 sorted lists. So in a way, this is a standard application of our merging algorithm. We can just go through from the top and always take the smaller one. The tricky bit is that we want to not spend a lot of time in the comparisons. Because these are strings, they could have long common prefixes, so we might have to compare a lot of characters if we do this naively. What will turn out to work is we use the standard sorting algorithm, the standard merging algorithm from merge sort, but we use a trick to speed up comparisons, which is similar to what we've done just in step 2 before. So let's try to do that. So here's a sorted prefix. This is the overall smallest taken from here, then this, then this. The first interesting one is this one, where we have to see that AH comes before HN, AN. Then comes AN. And now what's the next? Is it ananas man or as man? Well, I guess you know, but let's suppose the algorithm doesn't. So it has to compare these 2 suffixes. And the idea will be to apply the same trick as before. The trick being, look at the first character. If they are not equal, you're a happy man and you know what to do. If they are equal, you chop off that first character and keep looking. So in this case, they are the same characters, so we have to keep looking. So we chop off the first character and look what happens. And so in this case, we end up from a green with a blue one and from a blue with a green one. And we have gained nothing, because we still cannot compare those 2. That's a bummer. The trick here is to go 1 further character, and then it always works. I'll comment on that after the example. So if you take those 2 that we still could not compare, and you do the trick 1 more time, you're always guaranteed to end up with 2 blues, either after the first or after both steps. And once we have the 2 blues, we can use our rank array and look which one's smaller. And well, in this case, then that went all the way back. Nope, that's not what I wanted. I thought I put the the result up there. Too bad. We can always use at most 2 steps, and then we know what the smaller of the 2 is. And if you don't see why it helps to draw the picture of the different cases. So you have 2 suffixes that are of some different length. Now remember, there's always 2 positions that are blue, and then comes 1 green position. The reason why I'm drawing these lines across both is to emphasize that these are the same positions. If you right align the strings, these are the same characters, and so the pattern of 2 blue, 1 green is the same across the 2 strings. I don't know, okay. This is green. I guess this is green again. Blue, 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 blue. So you can have different cases. You can start, one string will be blue, one will be green, otherwise you already know the result. So you can either have 2 blues here or 1 blue. If you have 2 blues, like in this case, and you chop off the first character, you end up with blue, blue. So that's the case where it immediately works. And the other case is when you have just a single blue. Let's see if I can do that. If that's the case and you chop off the first 2, you just reverse the colors. You have green and blue. But if you do it another time, you're again into 2 blues, right? And these are really all cases that are possible, apart from symmetry. So the same step, the same trick works for this step. You just have to go 1 more character before you can decide it. But then you can still do merging in linear time, because each comparison takes constant time overall. It might be comparing the first character, maybe looking at the next, maybe looking at the next. But after 3 steps, you're done.